Hi again. There are only 5 things you need to know about circuits. The first thing is what happens if you apply a voltage V across the two ends of a resistor. Meaning you have a resistor with resistance R, what is the current I that will flow through it? The second thing you need to know is how to answer the same question for inductors. So you have an inductor, voltage V across it, inductance L, what is the current I that will run through it? The third thing you need to know, goes without saying, is of course what happens when you have a capacitor. Same question, you apply a voltage, what is the current that will run through it? The fourth thing, so these are the 3 basic components of circuits, but what about circuits themselves? So the fourth thing is what happens if you have a circuit. Think of circuits as networks of interconnected components. So what happens if you have a loop in that network? What happens with voltages? How can you compute the voltage from one point to the other point in a circuit? What if you put a voltmeter there? And the fifth and last thing you need to know is what happens when you connect things together. And let us start giving a few answers. When you have a resistor, all you need to know is Ohm's law, which is this very simple algebraic equation. When you have an inductor, you have a differential equation. V equals L times the derivative of the current. And when you have a capacitor, the equation is this last equation. You will often have to turn it on its head, meaning that you will often have to solve for V, for the voltage. And you can do so very easily by applying on both sides of the equation the integral by integrating from 0 to t. We know from the fundamental theorem of calculus that this first integral is equal to so these are the 3 basic equations: Ohm's law, this equation, and these 2 equations, which are exactly the same. This is in differential form, this is in integral form. Now when it comes to loops in circuits, let's say we have a loop A, B, C, D, E, then Kirchhoff's voltage law, KVL for short, states that the directed sum of all voltages is equal to 0. So in that case, we have here, the equation becomes, if you sum up all the voltages from A to B, B to C, C to D, D to E, and E back to A, the sum is equal to 0. This means also that when you have a closed loop like that, the voltage from A to B can be written in this convenient form. Instead of going directly from A to B, you can go all around. You can go, instead of going from A to B directly, like that, you can instead go first from A to D, then from D to C, and then from C to B. And you sum up the voltages. The result will be exactly the same. And this is a very useful result in circuits. Then when you have multiple components connected together, the voltage at this point is of course the same voltage for all components, but we can say something interesting about the current. So take for example a place in your circuit where 3 conductors meet. And let's say that I1 is the current of one conductor, I2, I3. One possible way to write Kirchhoff's current law, KCL for short, I will write here KCL, is the following. What comes in is equal to what goes out. So I1 is what comes in, and what goes out is I2 plus I3. Simple as that. The statement usually is phrased as the algebraic sum of all currents at the meeting point of multiple conductors in a network is equal to 0. This would mean simply that we bring all terms in the first hand of on the left hand side of the equation, and we would have, so several books write it like that. This is plus I1 because it goes inside towards the meeting point, and these are minus because they depart from the meeting point, but these are equivalent. I think it's more convenient to think of it like that. What goes in is equal to what goes out. And this is all the theory. You don't need to know anything more about circuits, and apparently you can solve a great variety of problems and derive differential equations for several problems. Let's start with an easy one. We have an RLC circuit. We apply a voltage V from one end to the other, and we have a current I running through the circuit. So what is the differential or integral differential equation that describes this system? This is the question. So when we solve an exercise, when we address any problem in circuits, we need to introduce points. It is very convenient to name a few points, give them names. And we will employ Kirchhoff's voltage law because we have a loop, and this is our loop from here to here. It is a closed loop essentially, because think of it like these two ends of the circuit connect to a battery. This is plus, this is minus, and this is the voltage. This is the voltage that we are allowed to manipulate. This is our input variable, but I will simply keep the sketch simple. So we have VAB is the voltage across the resistor. From here we know that it is RI. From B to C it is the current, we have the, voltage BC is the voltage across an inductor. So we have Li dot, this is the voltage across an inductor, and for the capacitor we have, now what do we have here? It's either this equation or that equation, whatever is more convenient for every problem. We will take that because we're looking for VCD, not for its derivative. So we have VCD at time 0 plus. And this is the integral differential equation that describes this system. There is nothing else to do. This is it. And it has I, it describes I in terms of V, which is the input variable. It is an integral differential equation, so if you very much like to write it in a state space representation, you need to go back to lecture number 2 and see how it's done. Or equivalently, we can approach the same problem in an alternative way. So again, the same equation, and we will write again. But instead of writing this whole thing, we will simply keep VCD, we will keep it VCD. We will not touch it. And we will solve for I dot. And this is equation number 1. However, what about VCD? Now, this variable satisfies this equation. And if we put them together, equation number 1 and equation number 2, we are able to define the state variable x, which is I together with VCD, and then this is the state space representation. Now the two approaches are absolutely equivalent. We can either use this equation and then derive at an integral differential equation as we did before, or we can do this little trick, not touch VCD yet, and then write down the differential equation that governs it. This is equation number 1, this is equation number 2, and then this is the state space representation. We solved an exercise using 2 different approaches. Now let's go to another example, because we have used 1, 2, 3, and 4, but we haven't used number 5, Kirchhoff's current law. So let's give an example now. Take again, we are allowed to manipulate the input voltage V. We have here R1, R2, L, C. We have the following currents running through the circuit. We have this I, let us call it I, and then IC and IL. Of course, by Kirchhoff's current law, by KCL, I goes in, IC and IL go out. Therefore, by KCL, we have this very simple equation over here. I will focus now. Let us give names to some points in the circuit. This will be A, B, and C, and point D. I will only focus on a part of the circuit, this part. I will focus on this part of the circuit that involves R1 and C. Then we have V, which is, of course, V from A to C, is the voltage from A to B plus the voltage from B to C. Voltage from B to C is the voltage across a capacitor. Again, I can write voltage across the capacitor at time 0 plus. So this is my first equation. However, I haven't said yet anything about the inductor, about this part of the circuit. And one thing I can do here is that I can write, again, I can invoke KVL, and I can write that the voltage from here to here is the voltage from here to here and from here to here. So VBD is equal to, and then this one by Ohm's law is, and BC, we know BC from before. We have an integral differential equation. So now this is almost good, because we have 2 equations that involve the following variables. Actually, excuse me, this should be IC over here, as it is here. These equations involve the variables IC, V, which is the input variable, and IL. However, they also involve I. But we know that I is IC plus IL. So I can rewrite this first equation. I will rewrite it at this position. And this will be my equation number 1, which involves IC and IC again and IL and the input variable. And equation number 2 is also fine. It only involves variables of interest and nothing more. If you like now, you can turn these 2 equations into a state space representation. The procedure is to take that integral and call it variable z of t, or however you wish to call it, and then follow the procedure we discussed in lecture number 2. Of course, this is one approach that leads to an integral differential equation. An alternative approach is to never have written the integral expression here for VBC, and instead we could have kept this term equal to VBC, which is just a variable. And then we have the differential equation, VBC dot is 1 over C times IC, this current. But you can do this as an exercise. You can follow exactly the same steps as we did in the previous exercise. Now, surprisingly, all the discussion about circuits boils down pretty much to these 5 essential things, especially when it comes to the study of capacitors, inductors, and resistors, which are the most common elements in simple introductory circuits. So that's it for today. Thank you very much for watching, and goodbye.